Hello guys, in this lecture we're going to continue our discussion about AC circuit analysis. So first we're going to review the basic concepts that we studied last lecture. Then we're going to go and start solving, examples with AC circuits. So as you see in this slide here, we discussed, that AC means alternating current. So basically, any signal like a voltage or the current is alternate with time, is it changing with time? And usually, our power generators, generate like sinusoidal forms. So the shape that came from the power generator, the electric generator, the source, the voltage source is like the voltage is changing in a sinusoidal wave with current. Okay, just like that, as we see here. Okay. Uh, so this is, as you see, periodic signal, okay, and usually start at zero. But sometimes, the signal doesn't start at zero, okay? And in that case, we say like there is a phase, okay, like that case here. So A of t or V of t, whatever, equal to some maximum sine omega t, and we say that omega is 2 by f, and f is the frequency. And in our case here in US, it's 60 hertz. Okay. And phi here is basically the shift. Okay. And the shift here basically before zero, so it's positive. If it start after zero, then we say it's minus. And we discussed last time why it's positive, why it's minus, last lecture. So you can go back and review that if you want. Okay. But we said like, using sign functions in our analysis will complicate the analysis. So we basically convert that sign, form, which is basically the real form, into something that is easy to manipulate and easy to work with mathematically. Okay. And this is basically was a complex form. Although it's called complex, but it will make like our life easier when we do like the analysis. Okay, so we're gonna write Vm sine omega t plus theta as Vm divided by square root of 2, and we said like Vm is the maximum value of the sine wave, like this value here. This is the maximum. VM or AM, whatever you call it. Okay. And we convert it to what is called RMS. Again, review our last lecture to know, to review or refresh your information about this, these terms. And the RMS value of any max value is VM divided by square root of 2. Okay. And just here in US, usually the outlet in your wall here is basically 120. This is the RMS value. So if you really measure, the outlet electricity that you have in your home, if it will be 120 RMS, and if you see it on like the actual form, it will be 170, which is 120 multiplied by square root of 2. So this is the VM divided by square root of 2, and then the shift phi or theta, we put it in like a polar form using exponential with j, and j here is, j is equal to like square root of -1. This is what makes it complex number. Okay. And this polar form can be written in an angle wave, in an angle form, like Vm divided by square root of 2 and angle theta. Both are the same. And theta here basically is a phi, Okay. Complex numbers has two forms, as we also see last lecture, it can be like in a polar form or a rectangular form. And in that case, the rectangular form, for example, can be written as x plus jy. And x, we call it like the real part, and y is the imaginary part. Okay, and we learned last lecture how to convert, from from polar to rectangular and rectangular to polar. But the good news is we will not use that, frequently in our course. Okay, this is just for your information, just in case you don't have the tools that I'm gonna teach you today. You can do it yourself. Okay, and just to complete the picture for you, we use the polar form when we do like multiplication or division. Like for example here, if we want to divide V1 angle theta 1 by V2 angle theta 2, then you just divide the amplitude part, V1 over V2, and then you subtract the angles from each other. So the final complex number here is V1 divided by V2, angle theta 1 minus theta 2. And we use the rectangular form, basically to when we do like subtraction or addition. So if we, for example, have like x1 plus jy1, and we want to add it to x2 plus jy2, then the final form will be x1 plus x2 plus jy1 plus y2. So you just add the real values together and the complex values together. Okay, good. So now, and also we discussed the impedance. Okay, what's called the impedance. So we said like in our AC circuits, there are new elements. We have what's called the capacitor, and we explained what the capacitor do. Okay, and the capacitor is defined by its capacitance C, which has a unit in farad. And we also discussed there is another element called inductor. And we also discussed what this inductor do, okay? And it's defined by its inductance. And the inductance has a unit of henries. Both Farad and Henry are just scientists, And both the capacitor and the inductor impede the current, just like the resistance, but with some other manipulation, like playing with the angle, the shift, between the current and the voltage. So it's not like the normal way of impeding current, like the resistance, but I mean, it doesn't reduce its value, but it do it in another way. Okay, and this way basically is, manipulating the shift, the angle between the voltage and the current. We discussed this also. Okay, so the impedance of the capacitor is minus J over omega C, and the impedance of the inductor is J omega L. Okay, and our old friend from DC, which is the resistance, has impedance as well, but its impedance just R. It will not change. Okay, good. Now let's see how to do circuit analysis, AC circuit analysis. Okay, that's our main topic today. So the good news is about AC circuit analysis, as you see here, that we can use any methods that we learned before in DC. Like you can use Kirchhoff current law, Kirchhoff voltage law, Ohm's law, nodal analysis, mesh analysis, whatever, Thevenin, Norton, whatever you used to do in DC, you can use in AC as well. That's the good news. Okay, and to make it just exactly like the forms or the circuits that we see before in DC, just to convert any impedance, any resistance, any capacitor or inductor into Z equivalent, impedance equivalent. Like for example, if you see a circuit, like if you see an inductor like this with L, just make it like that, and forget it was inductor, and call it Z. And the Z is the impedance of that inductor, which is J omega L. If you see a capacitor, replace it with a Z as well. Again, a box, Z equal to minus J over omega C. Just, give peace to your mind. And don't distract yourself. Just a box, I'm going to call it Z. This is the good news. Bad news. Unfortunately, dealing with complex numbers are so difficult. very difficult. And it's doable, of course, but it will it's very error prone. So but we have another good news, that the the analysis that we learn how to convert from complex to rectangular form, tabular form, all such stuff we will do online. We are electrical engineers, computer engineers. Our main target is to solve the circuits, not to learn math. So math for us is just a tool. So whoever gives us the final answer, that's it. We're gonna go with it. Our main problem is like the circuit analysis itself. So I'm gonna provide you with some online website that do complex number calculation for you. Okay, just like what we did with DC, I give you like the online calculator, which is Desmos. We still gonna use it. I just mentioned it here as well. Because we're gonna use it today, and also I give it like another website that do like solve linear equations together, which we usually do with nodal analysis and mesh analysis. And now there are other two websites. The most important one is that one here, which do the complex number calculations for you, either addition, multiplication, division, whatever. It will do it for you in a very fast way. You will not waste any time. And just convert from complex to rectangular form and vice versa. This website here will do this for you as well. Okay. By the way, you can also convert in the first website, but I usually use it on the second website. Now it's time for an example. Okay, we have an example here, and it's required from us to find the current I flowing in this branch here. Okay, I'm gonna do it in two ways, because again, we can use any analysis or any methods that we learn in DC in AC, and I'm gonna leave you with the homework to do it in a third way. And of course we have the final answer, so your way or your method in the homework should release or get the same number as I get. Okay, solution one, Ohm's law, the basic. Okay, so solution one, using Ohm's law. Ohm's law, I equal to V over R. This is in DC, my friend. Here, it will be I small equal to V over Z, the impedance. We generalize anything here, okay? So I, small letter I is just an AC current. Small letter V is a DC voltage. And Z is a general impedance. It can be resistance, it can be inductor and resistance, inductor and capacitance, combination of all of that. That's it. Okay? It's a generalization. Okay. So, as we learn, we're going to replace any branch with a Z. So you have two branches here. The first branch on the far right will be, let's call it Z2. And the one in the middle, we're going to call it Z1. And we have here a source. And our source is our normal source. I mean, the standard source that you see at your home, which is like 120 RMS angle 60. So it's written here, the angle is 60. I'm sorry, the angle, the phase is 60, and the amplitude is 120. And if the frequency 60 hertz, then this is basically the standard electric voltage that you have at your home. Okay, good. And this is the current I that we wanna calculate. Okay, you have here two impedances in parallel. So basically we can reduce that in that form here. Z, this is Mr. I and Mr. V here. And I will be equal to V over Z, just Ohm's law, right? So we know V, but we don't know Z yet. Once we find Z, then we find the current I. So how can we find Mr. Z? Okay, okay. Z1, Z basically is Z1 in parallel with Z2. Good. What is Z1? Z1 is the impedance of the capacitor, which is minus J divided by omega C. Divided by what? By omega C. Okay, remember, omega is 2 by F, and F is 60 hertz here. And the C, it's given here 50 micrometer farad. Okay, this is very doable. We can calculate it, right? Let's do it. So we're gonna go and open our online calculator, desmos.com. So we have to multiply the by. You can just write a by, it will be by. And then F, which is 60. Then we have, you can also copy this because we're going to use it again. And multiply the by C. And the C is actually omega C, I'm sorry. Omega is, omega, yeah, multiplied by C, and C is 50 microfarad. So micro, we're going to convert it to farads. So we should divide it by 1 million, right? So actually, we can do that in that way. So we can use 1 over and take all of that and put here of that. And we can divide the 50 by 1 million. 6 zeros, yeah, 53.052. So Z1 is actually minus J 53. Let's me get it again. 53.052. 53.052. Okay, that's basically, and so good. Now Z2. For Z2, it's J omega L plus R, the resistance. So R is 20, that's good. Now J 2 by 60, and the L is 100 milli. So 100 multiplied by 10 to the power of minus 3. So Z2 equal to, again, we're going to use our Desmos here. So you can take this as a copy and just leave it, don't modify it. So you can, if you want to review, just go back and review it. And we're going to multiply by 100 milli. So basically 100 and divide by 1000. Okay, 37.67, I believe. Check back. Yes, 0.7. This is J, and the R is 20. So 20 plus J 37.7. 20 plus J 37.7. That's basically Z2. Now we can use, so Z, now we can calculate Z. Z is equal to Z1 parallel with Z2. So Z1, Z2, just like DC plus Z1, Z2. And now it's time to use our online complex number calculator. So we're gonna go here, and this guy, yep, this guy. Okay, so we're gonna put this on the side here. Okay, what we have Z1, and Z1, let's see. Okay, Z1 is minus J minus I, and this, in this website, you have to use I. So you can also write it in that 53.052. This is and Z2 is 20 plus 37.7 I, and then big brackets and add them to each other. So we're gonna just take them, copy and paste. We will not write again, not to do any other mistakes, and just hit calculate, and that's it. You got it. This is basically the answer, and you got the answer actually in two ways, in two forms. You get the rectangular form, and you get also the angle form, or basically the polar form. Okay, which one is better for here in that case? Actually, the polar form, because at the end we're going to divide the v by z, right? So we're going to take the angular form. So d is equal to in the angular form 89.7.8. You just can, approximate this. Angle 9.33. Okay, that's basically z. Now I equal to v, which is 120 angle 60 divided by 89.8 angle 933. Okay, how we do that? That's very simple. 120 divided by 89.8, and the angle will be 60 minus 9.33. Desmos Demos. So we're gonna go here, and 120 divided by 89.9, that's 1.33, and the angle is much easier, which is basically 60 minus 9.33, which is 50.67. Good. Now we should ask ourselves a question. Is this the correct answer? It is the correct answer, but for now it might not be correct. There might be some mistakes. So you can review your answer. But you can do another way. You can solve the same circuit with another solution, with another method, and it should replicate, you should get the same answer, right? Solution 2, I'm gonna solve this using the nodal analysis. Nice. So this is our circuit. Z1, Z2, and our source, our voltage source, V. Okay, and this is the required R. Okay, so what we learned before in the nodal analysis, first we look at the nodes. Look and find the nodes. And here, if you look, we have two nodes. We have this node here, and we have this node. Okay, we have two nodes. So we have two nodes. Second step, assign a ground. Assign reference. One of the two nodes will be a reference, and our reference usually ground. Can we do any of them? Yes, you can do this one as a ground, and you can do also this one as a ground, and you use the second one or the other one to solve the circuit. What is the difference? Basically, the voltage will be different, of course, but the voltage difference will be the same. If you calculate I will be the same, so don't worry. You can use this as a ground, or you can use this as a ground. That's fine. Try both. I'm gonna do this because I usually put the ground, at the bottom, but you can do the other one. Okay, and we're gonna call this V, for example, or V1, whatever, So we're gonna call this the current in impedance Z1, I1, and the current in impedance Z2, I2. And we're gonna solve, this is the third step here, KCL at node V1. Okay, so KCL, Kirchhoff current law, will give us I equal to I1 plus I2. Just as a revision, what's entering the node equal what's going out of the node. Because we have like charge, conservation of energy and the charge and particles. So the particles enters, the electrons enters the node equal to the electrons going out of the node. Okay? Good. What's I? Actually, we don't know I, right? This is basically what we want to do. But we know I1. What is I1? It is V1 divided by Z1, right? What is I2? Again, it's V1 divided by Z2. You can do it in another way. You can say like V1 minus 0 over Z1, right? And this one is basically V1 minus 0 over Z2. But, now we are experienced. We have like many lectures in DC, so we know how to do that in details. Okay. Now, if we get V1 over Z1 and V2 over and V1 over Z2, we're gonna get I, right? That's what we're gonna do now. So let's calculate V1 over Z1. What is V1? So I equal to V1. Actually, V1, if we look at it, V1 is the same voltage as V, right? This is just one node. Again, as we learn in our circuits, we don't care about the geometric shape of the wires. Any wire in a circuit for us is a short circuit. So the voltage here basically the same voltage as V1. So actually V1 is, V, which is 120 angle 60 divided by, and the Z1 is the reactance or the impedance of the capacitor, which is minus J over omega C. What is V1 again? 120 angle 60 over minus J, no, sorry, 20 plus J omega L. Remember, we have omega C from before, we have omega L from before, so we can write this as 120 angle 60 over minus J 53.52 plus 120 angle 60 divided by 20 plus J 37, I believe, 0.7. Okay, and now we're gonna use again our online complex calculator to solve this. But we should convert the 120 angle 60 into a rectangular form, or convert these two, right, to polar form, whatever you like. But if you do the first one, it's just one conversion. If you do the second one and convert the rectangular to polar, you're gonna do two conversions, more time, right? So we're gonna do the first one. So we go to again this website here, which is like for conversion. So I'm gonna put like enter radius 120, enter angle, which is 60, polar to rectangular 60 plus 103 point. So this guy 120 angle 60 is actually, sorry, we can just bring this to the side. Oops, it goes away when it goes. It is actually 60 plus 103.9 and J here. Okay, now we can use our online calculator to solve that. So mm, 60 plus 103.99, and this will be divided by, and luckily we have it from before, 20 plus J, 37 plus 7, okay? And here this will be plus, because we're gonna add, right? So we wrote this already, now we write this. So again, we take this as a copy, we put it take this as a copy. Can we put it here, right? And remove this one. Can review very quick. 60 plus 103.9 I or J divided by 20 plus 37.7 plus the other component, which is this one here. Yeah, it's right. Let's calculate. Okay, the result. Okay, so basically, so the result, which is I, equal to sorry. Here is, we're gonna go with the polar form, like what we did in the first one. So 1.33 angle 50.25. Let's look. 1.33, 1.33. 50.67, 50.25. Bad? Not bad at all. That's perfect. So your homework now is to do the same circuit using mesh analysis. Okay, guys, thank you very much for watching and see you in the next video. Bye-bye.